I hope you find all of the exercises in this book to be enjoyable and interesting and insightful, but I think you're really going to like this one. At least I really like this exercise, and I hope you do too. Okay, you know that I really like creating random matrices that have specific properties that I impose. They should have specific rank, specific correlation structure, specific eigenvalues. I want to specify the properties of these random matrices. And here again, we are going to create a random tall matrix with a specified condition number. So remember, the condition number is like a measure of the spread of the information in the matrix. It is literally the ratio of the largest singular value to the smallest singular value of a matrix. And the reason why it's important is that matrices with really large condition numbers have a lot of stretching in one direction and very little stretching in another direction, or they might be completely compressed in another direction if they are singular. And matrices with a really high condition number can be unstable. They can be difficult to work with. They can cause inaccuracies in numerical computations like least squares fitting, for example. So condition number is pretty important. And if you really want to get into the nitty-gritty of really understanding and simulating data to understand analysis methods, it's useful to know whether a particular method or transformation that you are interested in can also work for high conditioned matrices. Okay, so with that in mind, what I want you to do is basically reproduce this figure. So here I have a random matrix A with a condition number of 42. Here is the U matrix. It has a condition number of 1 because it's orthogonal. So all of its singular values are 1. So the ratio of the largest one to the smallest one is 1. Okay, and then here is the sigma matrix. And this, of course, has a condition number of 42. Now, I'm not going to tell you exactly how to create this matrix, but I am willing to give you a hint. So if you do not want a hint, if you just want to try working through this and crafting an algorithm to create such a matrix, then pause the video now or like turn down the volume so you don't hear me. Here is the hint. The hint is that you can start from these two matrices, U and V transpose, or V, and then for sigma, remember the idea of a condition number is that it equals the ratio of the largest to the smallest condition number, singular value. All the other singular values don't actually matter. So for example, if the largest singular value is 84, and the smallest singular value is 2, then that ratio is going to be 42. So that's a little bit of a hint. I hope that helps. Okay, now I will switch to Python and I'll show you how I crafted this matrix. So we need to create 3 matrices. 2 matrices are just totally random numbers, but they need to be orthogonal. And I create random orthogonal matrices by taking the QR decomposition and then, of random numbers. The only trick here, I think, is to make sure that you are creating U and V transpose to be the appropriate sizes. So M by M and N by N. Of course, for a square matrix, those are identical. Okay, and then we need our vector of singular values, which we convert into a matrix. Now here, as I mentioned in my hint a moment ago, the key is that we don't actually care what all of the singular values are. The only 2 numbers we care about are the largest one and the smallest one. And that ratio needs to be 42, or whatever number you specify. So how do you get a ratio how do you ensure that the ratio between 2 numbers is a number that you can specify? I mean, there's a million ways you can do it, but the easiest way is just to have the denominator be 1. Super simple, right? So the denominator is 1, the numerator is the condition number. And then all the other singular values will be just linearly spaced numbers between them. It doesn't matter what these other numbers are. Okay, and then, you also need to be mindful that the number of non-zero singular values corresponds to the smaller of M or N. Okay, so this creates a vector, and we actually need a sigma matrix because I'm going to implement this as matrix multiplication. So here I create a zeros matrix, the same size as matrix A, and then I fill in the diagonal of sigma according to little s, which is these numbers here. Okay, and then I create the matrix by multiplying these three matrices, standard SVD theory. And then here in the titles of each subplot, I am computing the empirical condition number. So I'm not just printing out this number, this number here. I'm actually just computing the empirical condition number of these matrices. And then we get a result that looks like this. I think this is super neat. I hope you enjoyed working through this exercise.